Hello and welcome to the world of chemistry. In our last talk we talked about chemical reactions and you saw several of them. This video I want to go a little in depth of various chemical reactions. The first chemical reaction I want to consider is a simple replacement, and this will be a single metal pure element, potassium, reacting with water, which is a compound, to release another element, hydrogen, and have a compound, potassium hydroxide. Let me write the simple rules of that reaction on the board. We write it like this. Potassium is the symbol K, and it is a solid, and it is a metal. It's a type 1 in group 1 over here. I'll show you potassium. It's in the first column. And we're going to add to that water, H2O, and remember it's a liquid. Remember the subscripts describe it, because a chemical reaction, a chemical equation is to describe something that's physically happening. So this reacts, and what happens is that potassium is going to replace hydrogen, and you will get hydrogen, which is a gas, plus potassium hydroxide, which is a solution. Aqueous means it's in solution. So this is our chemical reaction. In order to write a chemical reaction, you must write all of the reactants correctly. The reactants are those over here, and all the products with their correct formulas over here. And then we have to proceed to balance. But first of all, let's take a look at this reaction. And I'm going to ask my lab assistant here to do this. First of all, we'll have her work here and get a piece of potassium. The potassium is stored under oil. It cannot be exposed to the air. And when she takes out a piece of potassium, I'm going to have her cut it in half, and hopefully you'll see it's shiny. She's blotting a little of the oil off of it, and then she's going to cut it in half, and hopefully we'll be able to see the shiny part to help identify. That's one property of metals, that they are shiny. And you expose the shiny surface? Yes. Okay. So she's putting part of that back in, and then she'll put the piece of potassium in a beaker over here where we have water. All right, is everyone okay? What you saw, the reason you see a little smoke is because there was still oil on the surface. Had we gotten a little bit cleaner, and you can kind of smell it, but I know you can't smell it, but we can kind of smell oil. Now, to show you that potassium hydroxide was formed, I'm going to use an indicator, and I'm going to use phenolphthalein. It turns pink when it's the base. So I'm going to ask you to add a little bit of phenolphthalein to that to show you that potassium hydroxide is a base and acid. We'll get to that classification. So it's very pink, meaning it's very basic. So you think about what we did. We took a metal, potassium, and we replaced the hydrogen and set the hydrogen free and produced a base. And a base is a metal with a hydroxide. So, okay, thank you. We can take this out of sight. Everything look okay? Good. All right. Incidentally, had we used sodium, it wouldn't have reacted quite as violently, because if you look at this chart, lithium would react with water slowly. This would react a little bit faster. Potassium would react really fast, and that's the one you saw. And I don't even want to talk about rubidium and cesium. They would be immediately react. So the next thing that we really want to do is, this equation is written correctly, but it is not balanced. And so in order to balance the equation, I want to go through that with you, is that we have to decide, count the atoms of each element. So I make a table I call the ERP table. Elements for the reactants and for the products. And this is just a kind of a table to help you keep track of things. Okay? So in the elements we have a potassium, we have a hydrogen, and we have oxygen. And then the reactants are over here, or the products are over there. So I simply count them. I see I have 1 potassium. And I have 2 hydrogens. Subscript gives me 2 of these, and I have 1 oxygen. Then I go over to the products, and I see that I have 2 hydrogens. I have 3 hydrogens. Tricked me. 2 hydrogens plus this one, so I have 3 hydrogens, 1 oxygen, and 1 potassium. So we ask ourselves the question, is this equation balanced? Well, you can see there's disagreement between the number of hydrogens. So we have to think about what we have to do to correctly balance this equation. Now, when we balance the equation, we may never change the subscripts, because the subscripts identify what it is. If I say H2O2, I'm talking about hydrogen peroxide, so I may never change the subscripts. So I'm faced with the issue of this is coming from a subscript 2. So any number I put in front is going to make 2, 4, 6, 8 an even number. Over here, I have an even number, but then I have the 1 odd number. So my best bet is to try to make it even by putting a 2 in front of this potassium. I have to put it in front. Once you put a number up there, then you need to go down here and make the changes. I changed the number of potassiums that I have for the product, didn't I? I had 1, but now I have 2. So I now have 2. And now my hydrogens become 1, 2. This multiplies 3, 4. So I now have 4 of those. And my oxygens, I have 2. So it looks like I really messed things up. However, I'm going to be able to fix it pretty easily. Because if I look over here, if I would double this and double that, and they're together, hydrogen and oxygen, I could do it. So I'll put a 2 in front of here and then record the consequences. 2 times 2 is 4. 2 times the oxygen is that, okay? And then we look at the potassium. It's the only thing that's not balanced. See, 4, 4, 2, 2. And so I can come back here and I can simply put a 2 in front of here and that changes it. That equation is balanced then. So the ERP method just helps you tally. But remember, whenever you put a number in front, then you have to go back and take care of all of the elements in that compound. Do whatever it does to it. And so that's a way to balance the equation. It's important to be able to balance an equation in a correct way. Now, what does this equation mean? I can interpret this equation, I guess, says it means 2 atoms of potassium react with 2 molecules of water to form 1 molecule of the diatomic element hydrogen and 2 molecules of potassium hydroxide. But remember that counting atoms is very difficult. And so I could just as well say 2 dozen react with 2 dozen, react with 1 dozen, react with 2 dozen. But even better, since we're chemists and we think of beaker only talks in terms of moles, I could say 2 moles of potassium react with 2 moles of water to form 1 mole of hydrogen plus 2 moles of hydroxide. This is an important interpretation because it's going to enable us to be quantitative about a chemical reaction. From this, I can write a whole lot of equalities. I could say 2 moles of potassium in this reaction is equal to 1 mole of hydrogen. Or I could say, 2 moles of water is equal to 1 mole of hydrogen. So I could do this, relate each substance to all the other substances from this. Important idea, though, is that a mole is a count, just like a 1 is, and a dozen. And so when we do this a little bit later, we are going to actually convert these moles to moles of that. This little subscripts is called stoichiometry. It means the little numbers that you put in front of the compounds to balance the equation, the stoichiometry. So it's by stoichiometry that we're able to relate moles of one kind of substance to moles of another kind of substance. Now, how could I ask a question, a multiple choice question, because you know most of your quizzes are multiple choice. How could I ask a question without having you actually to write an equation and balance it? Well, I might ask, what is the coefficient of water in the balanced equation? Knowing that, you'd have to look up here in the balanced equation and say, well, the answer would be 2. So I could do that. I could ask another way it's done. What is the sum of the coefficients in the balanced equation? Well, that's a little bit harder because you have to say that it's 2 plus 2, don't forget, plus 1 plus 2. And so therefore, the sum of the coefficients is 7. So this is a way that we can have you balance equations and then just answer multiple choice, which is easily great. I might ask you what's the coefficient of a particular substance, or I might ask you what the sum of the coefficients are. And don't forget, if it's not written, it means 1. Okay? Let's move to a little bit more idea of stoichiometry. That means the reactions. Let's suppose that we're going to make some wonderful substance. And that substance is made out of one heavy, big paper clip and 2 little ones. Just polish, she'll make me a compound out of that. We'll put those together. We'll call it a gizmo. It consists of 1 big one and 2 little ones. You could even almost think of this as a water molecule, 2 hydrogens and an oxygen. And so I start to think about this thing. How many would I need? For instance, if I have 3 of those and 10 of these, Paul, you're good at math. How many could I make? There's 2, 4, 6, 8, 10. Okay? She's sorting them out there. What happened? What happened was that I have too many of the little ones. So it's important for you to understand that in this chemical reaction, if the big paperclip was one substance and this little paperclip was the second substance, it'd be balanced by 1 to 2 stoichiometry. And if I buy more paper clips than I need, these are just extra. So what we would say in a chemical reaction, we couldn't make any more of these gizmos because we ran out of big paper clips. So that's the limiting reactant, and the other is excess. So if you really want to be exact about chemistry, you don't want to buy any more than you need. And so you have to count the ratios. And that's what this chemical reaction will tell me, that I need exactly 2 moles of that to react with 2 moles of that. It doesn't make any sense to have more. I want to show this to you. Here is a series of chemical reactions. I'm going to write this chemical reaction on the board. What this is it's lead 2 nitrate. So lead has a +2 valence. Remember, it's a type 2 metal. Lead, Roman numeral 2 nitrate, and it's aqueous. Let me show you these substances. You made a solution of 1 molar of the lead nitrate, and I made a solution of the potassium iodide, right there. Equal concentration solutions. So we have the lead nitrate plus the potassium iodide. Potassium is a type 1 metal with a +1. Iodide is the -1 ion, so it's aqueous. So we have an exchange. The lead goes with the iodine to form lead iodide. Now, lead is lead Roman number 2, and iodide is -1, so I'm going to have to take 2 of them. Remember that system? And it is a solid. So I think I have it right. The lead went with the iodide to form lead iodide, an insoluble precipitate, and their potassium is going to go with the nitrate. So I can't go any further there, but it's plus potassium nitrate, which is 1 + 1 - 1, and it's aqueous. It's not a solid. So this is a reaction that we have. I'm going to ask you, is this reaction balanced? Well, you can do ERP, but we'll just do it quickly. PB, NO3, K, and I. Now, one of the things that you notice is that I'm keeping the polyatomic together. And when you're doing that, it makes it easier to balance. Don't separate it out into nitrogen, oxygen. How many do I have as a reactant? I have 1 lead, 2 nitrates, 1 potassium, and 1 iodine. How many do I have as a product? I have 1 lead, 1 nitrate, 1 potassium, and 2 iodides. So now you see I have a problem. But it's not very difficult to fix. I put a 2 in front of the potassium, right here. I'll be changing to have 2 iodides in the reactants, and I'll be changing to have 2 potassiums. Okay? Well, that didn't quite do it. I have 2, 2, 2, 1, 2, 1. So if I could do something for the potassium and the nitrate, if I could do something for that, I should be able to do it. So let's look over here and see if I can put a 2 in front of that. So I have now, for the products, I have now 2 potassiums and 2 nitrates. And I believe that does it. 1, 1, 2, 2, 2, 2, 2, 2. So this equation is balanced by putting a 2 in front of the potassium iodide and a 2 in front of the potassium nitrate. Takes a little practice, but once you get onto it, it's kind of fun. Okay. So in this particular chapter, we've got to deal with quantity. And what I'm trying to show you is this particular demonstration is this reaction with lead 2 nitrate and potassium iodide. And I've added equal amounts of the lead 2 nitrate, 4 drops. And then I went back and added 1 drop of the iodide, 2 drops, 3 drops. When I would get to the 4th test tube, if that were the stoichiometric correct amount, I should get the same amount of precipitate, 1 to 1. See, 4 drops of one and 4 drops the other. I should have the maximum amount. But what happens is that you actually have to get to the 8th test tube. Here's 1, you can hardly see the lead iodide, no reaction. 2, only a little bit, and that's only 1 drop of the Ki. 2 drops, 3 drops, 4. 4 and 4, that'd be 1-to-1 stoichiometry. 5, 6, 7, 8. And so what you see is over here, when I've added the 8 drops, you see the max amount of precipitate. Beyond that, if I add 9 drops, 10 drops, it's not going to change anything because I just have excess Ki. So there is such a thing as having the maximum stoichiometry, the right amount of this to exactly right to produce that. If you lack this, then you'll have then a limiting reactant. So last of all, I think I want to do is I want to take a simple reaction and ask what will happen if we take this balance reaction. One of the reasons I'm doing this is so that you understand moles is important. It's central in chemistry. And so what I can do is I'm going to take calcium carbonate. This is a +2, and this is a -2, so that's the formula for calcium carbonate. It's a solid. And if I add to it HCl, hydrochloric acid, and it'll be aqueous, it'll be a solution, I will get bubbles. This is a classic test we do in geology for limestone. I'll get bubbles of carbon dioxide, that'll be a gas, plus I'll get calcium chloride, plus I'll get water. Now, I can balance this equation because calcium chloride is going to be aqueous, and this is going to be liquid. I can balance the equation because I've written all of the reactants correctly, all the products correctly. So all I have to do is calcium, and the reactant is 1, the product is 1. Carbon, reactant is 1, product is 1. Oxygen, the reactant is 3. The product is 1, 2, 3. Hydrogen, reactant is 1. The product is 2. And chlorine, down at the bottom, the reactant is 1, and the product is 2. Okay. So what it seems to me is that everything looks good until I see both these out. Well, there's a very simple solution. These are together, and if I double it, then I have changed this one to 2 and this one to 2, and this is a balanced chemical reaction. So the balanced chemical reaction tells me that 1 mole of calcium carbonate reacts with 2 moles of hydrochloric acid to produce 1 mole of carbon dioxide. So one of the things I'd like to do is go from mole of this to grams. In order to do that, remember in the last chapter we talked about the molar mass. We have to figure out the formula weight of calcium carbonate. And I'll kind of do this quickly. I will look up calcium, and I'll say that calcium is, I'll ask Paula to do this on the calculator along with me. Make sure I get this. Calcium, I see, is 40. Carbon is 12. And oxygen is 3 times 16, 48. And we add that together, we get 100. Let's use the calculator. Okay. So what we can say is 100 grams of calcium carbonate equal 1 mole. Okay? And let's say that I have excess of this. Plenty of it. Now, it's not going to be the limiting reactant. Now, my question is, how many grams of carbon dioxide can I produce? Okay? Let me restate that question so that we know where we're going. Given 100 grams of calcium carbonate, I want to know how many grams of C carbon dioxide. So what I need to do is I have to convert this to moles. And because I started with 100 grams of calcium carbonate, and I know the 100 grams equal to 1 mole, I could simply do that. 1 mole per 100 grams. Now, the next thing depends on the stoichiometry. I have to go from moles of calcium carbonate to moles of carbon dioxide. And I can see there's 1 mole to 1 mole from the balanced equation. So I say 1 mole of CO2 per 1 mole of calcium carbonate. That's the stoichiometry. Cancels, cancels. And now all I have to do is go from moles of carbon dioxide to grams of carbon dioxide, which I can get the molar mass of carbon dioxide, 44, 2 times 16 for the oxygen, 32 plus 12, 44. So 44 grams of CO2 per mole. So what we really have done is we've introduced a way to get from grams to moles, which we already know, and the stoichiometry allows us to go from moles to moles. Okay? And so really I could ask any question like that. I could say, if I have 2 grams of calcium carbonate, how much carbon dioxide? You do the same process. You convert the grams by dividing by the molar mass to moles. Then you'd use the stoichiometry to go from moles of that to moles of that. And then you'd use the formula weight of carbon dioxide to go back into grams. So this is the kind of problem that you're going to encounter in this chapter 8 that we're studying. Have fun with that, and have confidence that you really know that the chemical reactions are done quantitatively, and that you basically have to use this new conversion factor from a balanced equation. So we'll be balancing equations, different types of equation, and then we will be working with certain amounts to find out how much product we get. Extremely important thing in industry. If you're making something or if you're buying something, that you know that you get the right amount to get what you want, nothing extra. So good luck, have fun. I'll be posting some notes also to help you. Thank you.